Right now, photons of light are streaming through the darkness of space, carrying information about stars that died billions of years ago. Some of these particles have been traveling since before Earth existed. They crossed unimaginable distances, passed through clouds of gas and dust, survived the expansion of space itself, all to reach your eyes in this moment. But their journey will not last forever. The universe has an expiration date, and when that end comes, every photon of light, every particle of energy that has ever existed, will face a final reckoning. Scientists have calculated the timeline of cosmic extinction. The numbers reveal a truth more unsettling than most people realize. Light, the fastest thing in existence, the universal speed limit, the phenomenon that makes vision possible and connects us to distant galaxies, does not travel forever. Its journey has an ending. And understanding that ending requires understanding something profound about the nature of reality itself. If you are ready to discover what happens to light when the universe reaches its final chapter, settle in. Get yourself comfortable. Close your eyes if you wish. Let us begin a journey to the end of everything. The question seems simple at first. Where does light go? But hidden within those 5 words lies one of the deepest mysteries in physics. To answer it, we must first understand what light actually is. Not the simplified version taught in school, but the strange quantum reality that governs how photons behave when nobody is watching. Light is not a thing in the way most objects are things. You cannot hold a photon. You cannot slow it down or speed it up. A photon exists in a state that defies easy description. It behaves sometimes as a wave, spreading across space like ripples on a pond. Other times it behaves as a particle, a discrete packet of energy that can be counted and measured. This dual nature troubled physicists for centuries. It still troubles students encountering quantum mechanics for the first time. But here is what we know with certainty. A photon is a quantum of electromagnetic radiation, a messenger of energy that carries no mass. Think about that for a moment. Light has energy. It can push on objects. It can heat surfaces. It can cause chemical reactions in your eyes that create vision. Yet it weighs nothing. It carries no electrical charge. It is pure energy in motion, forever traveling at the speed that bears its name. This masslessness has profound consequences. Because a photon has no mass, it cannot slow down. From the moment it is born, whether from a candle flame or a supernova explosion, it travels at exactly 299,792,458 meters per second in vacuum. Not approximately. Exactly. This is not just the speed of light. It is the speed of causality itself, the fastest that information can travel through space. The ultimate cosmic speed limit written into the fabric of reality. Every photon moves at this speed regardless of its energy. A low-energy radio wave photon travels at the same velocity as a high-energy gamma-ray photon. The difference lies not in speed, but in wavelength and frequency. High-energy photons oscillate rapidly with short wavelengths. Low-energy photons oscillate slowly with long wavelengths. But all move at the same relentless pace through the vacuum of space. Now imagine you could follow a single photon on its journey. You cannot, of course. The observer effect in quantum mechanics prevents perfect tracking without disturbing the very thing you observe. But imagine it anyway. This photon was born in the core of a star 10 billion light years away. It emerged from a fusion reaction where hydrogen nuclei crashed together under immense pressure and heat, forming helium and releasing energy. That energy became our photon. It began its journey buried deep inside the star. The stellar interior is so dense that photons cannot travel far before being absorbed and re-emitted by atoms. They scatter randomly in all directions. A photon that will eventually escape and travel across the universe might spend tens of thousands of years just reaching the star's surface. It staggers outward through layers of plasma like a drunk person trying to find the exit from a maze. Each interaction changes its direction. Each absorption and re-emission might change its wavelength. The photon that emerges is not quite the same as the photon that began the journey. Finally, it reaches the surface. The density drops. The temperature falls, space opens up, and the photon, now free, begins its true journey across the cosmos. For 10 billion years it travels. It crosses the void between stars, regions so empty that it might go millions of years without encountering a single atom. It passes through clouds of gas and dust, some of which scatter it slightly, changing its direction but not its speed. It rides the expansion of the universe itself, space stretching beneath it like a cosmic treadmill that never stops moving. And throughout this entire journey, from the photon's perspective, no time passes at all. This is where physics becomes genuinely strange. Due to time dilation effects and special relativity, time stops for anything traveling at the speed of light. From the photon's frame of reference, its creation and its absorption happen in the same instant. The 10 billion year journey you observe happens in zero time for the photon itself. It is born and dies in the same moment, experiencing no duration between these events. The photon exists in an eternal now, outside the flow of time that governs massive particles. But you are not a photon. You observe from a frame of reference where time flows normally. And from your perspective, that photon traveled for 10 billion years before reaching Earth's atmosphere, passing through the air, entering your eye, and being absorbed by a molecule in your retina. The energy it carried, preserved across cosmic distances, triggers a chemical reaction. A nerve signal fires. Your brain constructs an image. You see a star. That photon's journey has ended. It gave up its energy to your eye. It ceased to exist as a photon. The energy transformed into heat and chemical potential. The information it carried, encoded in its wavelength and direction, became part of your conscious experience. Then that too faded as your neurons reset for the next signal. This is what happens to light in our current universe. Photons are born. They travel. They are absorbed. Their energy transforms, but never disappears. Energy cannot be created or destroyed, only changed from one form to another. This is the first law of thermodynamics, as ironclad as any principle in physics. But notice what drives this cycle. Stars create photons. Eyes and planets and dust clouds absorb them. The universe is full of sources and sinks, creators and consumers of light. The cosmic ecosystem processes light continuously, creating it in hot places and absorbing it in cooler places. Energy flows from high temperature to low temperature, spreading out, evening out, seeking equilibrium. This spreading is not random. It follows a deep principle called the second law of thermodynamics. Entropy always increases in a closed system. Disorder always grows. Concentrated energy always dissipates. This is not just a suggestion. It is a fundamental arrow of time. The reason why broken eggs do not spontaneously reassemble and why heat flows from hot to cold, but never the reverse. Right now, our universe is nowhere near equilibrium. Temperature differences exist everywhere. The core of the sun blazes at millions of degrees while the void of space hovers just above absolute zero. Stars burn. Galaxies spin. Black holes feed. Photons stream through the darkness, carrying energy from hot to cold. The cosmic machine runs on these temperature differences, these gradients of energy density. But gradients do not last forever. The second law ensures that they flatten out. Eventually, inevitably, currently, the universe creates new stars constantly. Not as quickly as it did billions of years ago, but the process continues. Every year in our galaxy alone, roughly 3 solar masses worth of gas collapse to form new stars. These fresh suns will burn for millions or billions of years, depending on their mass. They will create trillions upon trillions of new photons. The light show continues, but the fuel for star formation is finite. Hydrogen, the primary fuel for stellar fusion, cannot be replenished once consumed. When 2 hydrogen nuclei fuse into helium, that helium generally stays helium. Stars create heavier elements through fusion, working their way up the periodic table through carbon, nitrogen, oxygen, eventually reaching iron in the most massive stars. But once material is fused into these heavier elements, normal stellar processes cannot reverse the reaction. The hydrogen is gone. The universe contains a vast but limited supply of hydrogen. Currently, most of it remains unused, sitting in clouds of gas between galaxies or locked in stars that have not yet exhausted their fuel. But with every passing year, stars convert more hydrogen into helium and heavier elements. The supply dwindles. The countdown proceeds. Astronomers have calculated when star formation will end. The timeline depends on how quickly gas cools and collapses. The timeline depends on how efficiently stars form from available material and how much hydrogen is locked away in places where it cannot collapse. Current estimates suggest that star formation will peak and then decline over the next few trillion years. Some small, dim stars might continue forming for perhaps 100 trillion years. Beyond that, the process stops. No more hydrogen remains available for fusion. No new stars ignite. 100 trillion years. The number is so vast it defies intuition. The current age of the universe, from the Big Bang to now, is roughly 13.8 billion years. 100 trillion is more than 7,000 times longer than the universe has currently existed. Humans evolved from ape-like ancestors in roughly 6 million years. Complex life has existed on Earth for roughly 600 million years. The sun will exhaust its fuel and become a red giant in about 5 billion years, long before star formation ends. 100 trillion years from now, Earth will be gone, the sun will be gone, most currently existing stars will be gone, but a few final dim stars might still flicker in the darkness. Those final stars will be red dwarfs, the smallest and longest lived stars possible. They burn hydrogen so slowly that a single red dwarf might shine for 10 trillion years or more. When the last of these gutters out, when the final fusion reaction converts the final hydrogen nucleus into helium, when the last photon from the last stellar core begins its final journey into space, an era ends. The stelliferous era, the age of stars, will be over. The universe will enter a new phase. Darker, colder, quieter, and light's relationship with the cosmos will change fundamentally. But before we journey into that dark future, we must understand where light goes right now, in this current epoch when stars still burn and photons still flood space. Because the mechanics of light's journey today determine what will happen when the sources dry up and the cosmic light show finally ends. Consider the cosmic microwave background, the oldest light in the universe. These photons were born roughly 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely for the first time. Before this moment, the universe was opaque, a hot, dense plasma where photons could not travel far before being absorbed and re-emitted. But when atoms formed, suddenly space became transparent. Photons decoupled from matter and began traveling freely. Those photons have been traveling ever since. We detect them today as microwave radiation coming from all directions. They have traveled for 13.8 billion years, crossing the expanding universe, their wavelengths stretched by the expansion itself. They were born as visible and infrared light, but shifted into the microwave range as space expanded beneath them. This stretching is called cosmological redshift, and it reveals something crucial about light's fate in an expanding universe. Imagine a photon traveling through expanding space. As space stretches, the photon's wavelength stretches too. A photon born as blue light becomes green, then yellow, then red, then infrared, then microwave, then radio wave. Its energy decreases as its wavelength increases. The relationship is exact. Energy equals Planck's constant times the speed of light divided by wavelength. Double the wavelength and you have the energy. The cosmic microwave background photons have lost energy this way. They were born hot, carrying the thermal energy of the early universe plasma. Now they are cold, carrying an energy corresponding to a temperature just 2.7 degrees above absolute zero. Space expansion stole their energy, not through absorption or collision, but through the stretching of space itself. This process continues. Right now, as you read these words, the cosmic microwave background is cooling. Its photons are losing energy. Their wavelengths are stretching. In another trillion years, the cosmic microwave background will be colder, dimmer, harder to detect. Its photons will have shifted into longer wavelengths, carrying less energy. Eventually, after timescales we will explore later, these photons will become so stretched, so depleted of energy, that detecting them becomes essentially impossible. Where did their energy go? Into the expansion of space itself. This sounds like a violation of energy conservation, but it is not. In general relativity, energy conservation works differently in an expanding universe. The expansion can create or destroy energy in ways that seem impossible in everyday experience. Photons losing energy to expansion is one consequence of this strange cosmic accounting. Currently, the universe contains photons of every wavelength imaginable. Gamma rays from supernovae, X rays from matter falling into black holes, ultraviolet from hot young stars, visible light from stars like our sun, infrared from warm dust clouds, microwaves from the cosmic background, radio waves from pulsars and active galaxies. This is the electromagnetic spectrum, and every part of it carries information about the universe's current state. All of these photons are traveling. Some will be absorbed by dust or gas. Some will fall into black holes and disappear from the visible universe. Some will travel for trillions of years across expanding space, their wavelengths stretching, their energies diminishing, until they become almost undetectable whispers of their former selves. But new photons are being created constantly. Stars fuse hydrogen, atoms decay, particles annihilate. Each process releases energy, often in the form of photons. The cosmic inventory of light remains large because the sources remain active. The second law pushes toward equilibrium, but the universe is far from equilibrium. Energy concentrations still exist. Temperature gradients remain steep. The machine still runs. This cannot last forever. The fuel runs out. The stars die. The sources stop producing. And when that happens, when the last stellar fusion reaction sputters to completion and the last astrophysical photon source goes dark, light's story enters its final chapters. What happens then depends on which ending the universe chooses. And physics offers several possibilities, each with different implications for light's ultimate fate. Some endings are gentle, a slow fade into darkness and cold. Others are violent, a catastrophic tearing apart of space itself. One possibility involves the universe collapsing back in on itself, all the light that ever existed compressed back into a single point. We do not know which ending is correct. We can only calculate the possibilities and see where each one leads. Each path reveals something profound about the nature of light, energy, and existence itself. The journey to answer where light goes when the universe ends must pass through these possible endings. We must explore each scenario, follow the physics to its conclusion, and see what fate awaits every photon that has ever existed. Let us begin with the most likely scenario according to current observations. The one most scientists expect will actually happen. An ending called heat death, where the universe does not explode or collapse, but simply runs down like a clock that nobody wins. Where entropy wins its long war against order. Where every temperature gradient flattens, every energy source exhausts itself, and light faces its strangest fate of all. Not destruction, not absorption, something far more subtle and far more final. But to understand that fate, we must first understand what heat death actually means. What it looks like when entropy reaches its maximum and the cosmic engine finally, irreversibly, stops running. The universe will end. This much we know with certainty. What remains uncertain is how. For most of human history, the question did not even arise. People assumed the cosmos was eternal, unchanging, infinite in both time and space. The stars would shine forever. The heavens would endure. Nothing fundamental would ever change. Then in the early 20th century, astronomers discovered something shocking. The universe is expanding. Galaxies are moving away from each other. Space itself is stretching. And if you run this process backward, rewinding the cosmic movie, everything converges to a single point roughly 13.8 billion years ago. The Big Bang. A beginning. If the universe had a beginning, it can have an ending. The discovery of cosmic expansion changed everything. It revealed that the cosmos is dynamic, evolving, changing in fundamental ways over time. And anything that changes can potentially stop changing, can reach some final state, can end. But in how? The equations of general relativity, the mathematical framework that describes how gravity warps space-time, offers several possible futures. Each depends on factors we can measure, but have not yet measured with perfect precision. The density of matter and energy in the universe, the strength and behavior of dark energy, the curvature of space itself. These parameters determine which ending we get. Currently, four main scenarios dominate scientific discussion: heat death, big rip, big crunch, big bounce. Each represents a different solution to the equations, a different path the universe might take. And crucially for our question, each offers a different answer to what happens to light when the end comes. Let us examine each scenario in turn, not with overwhelming mathematical detail, but with enough physics to understand what actually happens to photons in each case. Because light's fate is written in these endings, encoded in the fundamental laws that govern energy and spacetime. The first scenario, and the one most scientists consider most likely given current observations, is called heat death. Despite the name, it has nothing to do with heat. In fact, it is exactly the opposite. It is the coldest, darkest, most featureless ending imaginable. Heat death is what happens when entropy wins. Remember that word. Entropy, the measure of disorder in a system, the quantity that always increases in any closed system. The reason why mixed coffee and cream do not spontaneously unmix. Why scrambled eggs do not uncook themselves. Why hot objects cool down and never spontaneously heat up. Entropy is not just disorder in the everyday sense of messiness. It represents something deeper. The number of ways particles can be arranged microscopically while producing the same macroscopic state. A system with high entropy has many possible arrangements. A system with low entropy has few. Ice has lower entropy than liquid water, which has lower entropy than water vapor. The molecules in ice are locked in rigid crystal positions. The molecules in vapor spread throughout available volume randomly. Many more microscopic arrangements exist for vapor than for ice. Therefore, vapor has higher entropy. The second law of thermodynamics states that in any closed system, entropy must increase or stay constant. It cannot decrease. This is not a suggestion or an approximation. It is as fundamental as any law in physics. More fundamental perhaps, because it emerges from statistical probability rather than being imposed by decree. The second law is simply the mathematical fact that systems naturally evolve toward states with more possible arrangements, and there are vastly more high entropy states than low entropy states. Our current universe has relatively low entropy. Stars concentrate energy in small regions of space. Galaxies cluster in sheets and filaments separated by vast voids. Temperature differences exist. Structure persists. Order remains, at least in pockets. But the second law demands that this order decay. Energy must spread out. Temperatures must equalize. Structure must dissolve. The universe must become more uniform, more featureless, more disordered. This is not optional. It is not something technology can prevent. It is built into the mathematics of probability itself. Heat death is what the universe looks like when entropy reaches its maximum possible value. When no further increase is possible. When every gradient has flattened, every energy source has exhausted itself, every temperature has equalized. When the cosmic system has explored every possible arrangement of its particles and settled into the vast sea of maximum entropy configurations. What does this actually look like? Imagine the universe in the far future, trillions upon trillions of years from now. All the stars have burned out, their fuel exhausted, their light extinguished. No new stars form because all available hydrogen has been fused into heavier elements or locked away in cold gas clouds that can never collapse. The stellar era has ended. What remains are stellar remnants. White dwarfs, the cooling cores of dead sun, like stars. Neutron stars, the collapsed cores of dead massive stars. Black holes, regions of space-time so warped that not even light can escape, and vast clouds of cold gas and dust, the debris of stellar death, drifting through expanding space. The white dwarfs cool over trillions of years. They start as incandescently hot, heated by the residual thermal energy from their stellar past. But with no fusion to replenish the heat, they radiate their energy away as infrared light, then microwave radiation, then radio waves, then eventually nothing detectable at all. They become black dwarfs, cold dark spheres of carbon and oxygen floating through space at just barely above absolute zero. Neutron stars follow a similar path. They too cool, radiating away their heat over cosmic timescales. Their exotic matter, compressed to nuclear densities, slowly releases its thermal energy to space. Eventually, they too go dark and cold. Black holes present a different situation. They do not cool in the conventional sense because they do not radiate heat in the conventional sense. Or rather, they do, but through a quantum mechanical process so slow and strange that it barely matters for black holes of stellar mass or larger. In 1974, Stephen Hawking discovered something remarkable. Black holes are not perfectly black. They emit radiation, not from inside the event horizon, but from quantum effects just outside it. The vacuum of space is not truly empty. It seethes with virtual particles that pop into existence in particle-antiparticle pairs and immediately annihilate. Normally, these pairs exist for such a brief time that they have no measurable effect. But near a black hole's event horizon, something strange can happen. If a particle-antiparticle pair appears just outside the horizon, one member might fall in while the other escapes. To an outside observer, it appears that the black hole has emitted a particle. This is Hawking radiation, and it carries energy. That energy must come from somewhere. It comes from the black hole's mass. The black hole slowly evaporates. For a black hole with the mass of our Sun, this process is extraordinarily slow. The Hawking radiation is so weak, so cold, that the black hole actually absorbs more energy from the cosmic microwave background than it emits. It gains mass rather than losing it. The evaporation does not begin in earnest until the universe cools to a temperature below the black hole's Hawking temperature. But eventually, after the universe expands enough and cools enough, even massive black holes begin to lose mass through Hawking radiation. And as they shrink, the process accelerates. Smaller black holes are hotter. They radiate more intensely. The final moments of a black hole's evaporation release a burst of energy as the last of its mass converts to radiation. The timeline for black hole evaporation is almost incomprehensible. A black hole with the mass of the Sun would take roughly 10 to the power of 67 years to evaporate. That is 10 followed by 67 zeros. A 1 with 67 zeros after it. To put that in perspective, the current age of the universe is roughly 10 to the power of 10 years. The time until all stars burn out is roughly 10 to the power of 14 years. Black hole evaporation happens on timescales so vast that our usual language fails. Supermassive black holes, the monsters at the centers of galaxies with masses millions or billions of times that of the Sun, take even longer. A billion solar mass black hole would take roughly 10 to the power of 100 years to evaporate. That number is called a googol. It is larger than the number of atoms in the observable universe. It is a timescale beyond human comprehension. But time, in this scenario, is unlimited. The universe keeps expanding. The temperature keeps dropping. And eventually, inevitably, even the largest black holes evaporate. They release their mass, energy back into space as a spray of photons and particles. A final fireworks display, watched by nobody, in a universe that has become almost entirely dark and cold. When the last black hole evaporates, something profound happens. The last major concentrations of energy in the universe disappear. What remains is a thin soup of particles, mostly photons and neutrinos, spread across expanding space. The temperature approaches absolute zero, not quite reaching it, because quantum mechanics prevents perfect stillness, but coming arbitrarily close. The energy density drops towards zero. The universe becomes cold, dark, empty, and featureless. This is heat death, maximum entropy, thermodynamic equilibrium, the end state of the second law's relentless march toward disorder. No temperature gradients exist. No energy flows. No processes can happen that would decrease entropy. The cosmic engine has stopped because there is no more fuel to burn and nowhere for energy to flow. And in this state, light exists in a strange liminal condition. Photons still exist. They have not been destroyed. Energy conservation forbids their destruction, but they are spread so thin, their wavelengths so stretched by cosmic expansion, their energies so diminished, that they become effectively undetectable. They fade into the quantum noise of the vacuum itself. Not gone, but unreachable. Not destroyed, but transformed into something so diffuse and cold that no process could ever collect them again into anything resembling light. This is the most likely ending according to current cosmological observations. Not a bang, but a whimper. Not an explosion, but an exhausted sigh as the universe runs down and stops. But other endings are possible. The equations allow different solutions if the parameters are different. And we do not know those parameters with perfect certainty. Dark energy, the mysterious force accelerating the universe's expansion, might not behave the way we currently assume. Its strength might change. Its nature might shift. And if it does, the universe's fate changes with it. The second scenario is called the Big Rip. It happens if dark energy becomes stronger over time instead of remaining constant. Currently, dark energy appears to be a cosmological constant, a fixed energy density that does not dilute as the universe expands. This causes accelerating expansion, but at a steady rate. If dark energy behaves this way forever, we get heat death. But what if dark energy grows stronger? What if its density increases over time, or its repulsive effect intensifies? Then expansion does not just accelerate. It accelerates faster and faster, runaway growth that eventually tears the universe apart at every scale. This process starts subtly. Expansion accelerates. Galaxy clusters that were gravitationally bound begin to be pulled apart. Galaxies that would have remained together forever instead separate. The night sky slowly empties as distant galaxies recede beyond the cosmic horizon, their light redshifted into invisibility. But it does not stop there. The acceleration continues to grow. Eventually, it becomes strong enough to overcome the gravity holding individual galaxies together. Stars are ripped away from galactic cores. The Milky Way, if it still exists in this far future, would be torn apart, its hundreds of billions of stars scattered into the expanding void. Still, the acceleration grows. It becomes strong enough to unbind solar systems. Planets are torn from their orbits. Moons are separated from planets. Objects that have orbited together for billions of years are violently separated as expansion overcomes gravity at smaller and smaller scales. The process continues all the way down. Expansion becomes strong enough to overcome the electromagnetic forces holding molecules together. Water molecules are ripped apart into hydrogen and oxygen atoms. DNA unravels. Proteins denature. Every structure held together by chemistry dissolves. Finally, in the last moments before the end, expansion becomes strong enough to overcome the nuclear forces binding atomic nuclei. Protons and neutrons are torn apart into their constituent quarks. The fundamental particles that make up matter are shredded by the exponentially growing expansion of space itself. This happens everywhere simultaneously. Within perhaps 1/1,000,000th of a second, the entire universe is reduced to a sea of free quarks and leptons, and then even those structures dissolve as space itself tears apart. The Big Rip, a violent, sudden, catastrophic ending where expansion becomes infinite in finite time. What happens to light in this scenario? During most of the process, photons behave normally. They travel through expanding space, their wavelengths stretching, their energies decreasing, just as in the heat-death scenario. The accelerating expansion makes this redshift more severe, cooling photons more quickly, but the basic physics remains the same. But in the final moments, something stranger happens. As the expansion rate approaches infinity, space-time itself becomes unstable. The smooth fabric of space develops tears and discontinuities. The notion of a photon traveling from one location to another becomes ill-defined when space itself is being ripped apart faster than light can traverse it. In the last instant, photons, like everything else, are shredded. Their wave functions are torn apart by the tearing of space-time. What happens to them, then, is unclear. The physics breaks down. General relativity cannot describe what happens when space-time itself ceases to be continuous. Quantum mechanics cannot describe what happens to quantum fields when the underlying space disappears. The theories fail. Perhaps the photons simply cease to exist when the space-time that supports them disintegrates. Perhaps they transform into something else, some quantum state that has no classical analog. Perhaps the question itself becomes meaningless when the arena in which physics operates, space-time itself, no longer exists. The Big Rip is dramatic but currently considered unlikely. Observations of dark energy suggest it behaves as a cosmological constant, not as something that grows stronger. But our observations cover only a tiny slice of cosmic history. Dark energy might change its behavior in the future. We cannot rule out the Big Rip with certainty. It remains a possibility, however remote. The third scenario reverses the story of expansion entirely. The Big Crunch. This happens if the universe contains enough matter and energy that gravity eventually overcomes expansion and pulls everything back together. In the current universe, this appears impossible. Observations show that expansion is accelerating, not slowing. Dark energy dominates over matter. The universe seems destined to expand forever, not to recollapse. But again, we do not know the future behavior of dark energy with certainty. If it weakens or reverses, if its repulsive effect diminishes, gravity might eventually win. In a Big Crunch scenario, expansion slows, stops, and reverses. Galaxies that are currently receding begin to approach. The cosmic microwave background, which is cooling in our current expanding universe, begins to heat up. Photons gain energy as space contracts instead of losing energy as space expands. Blue shift replaces redshift. The process mirrors expansion in reverse. Galaxy clusters merge. Galaxies collide and combine. Stars pass through increasingly dense regions of space. The night sky brightens as radiation that was previously spread thin becomes concentrated. As contraction continues, temperatures rise. The universe becomes hotter and denser. Eventually, it becomes so hot that stars evaporate, their atoms stripped apart by thermal energy. Matter breaks down into its constituent particles. The universe becomes a plasma, then a quark, gluon plasma, then something even more exotic as temperatures soar beyond anything we can create in particle accelerators. All the light that ever existed, every photon that ever traveled through expanding space, is still present but now moving through contracting space. Their wavelengths shrink. Their energies grow. Microwave photons become infrared, then visible, then ultraviolet, then X rays, then gamma rays of such high energy that they can create matter-antimatter pairs when they collide. The universe becomes increasingly opaque as it contracts. High-energy photons scatter off particles constantly. Space glows with intense radiation from every direction. No stars are visible because the background radiation outshines everything. The universe becomes a blazing furnace, hotter and brighter with each passing moment. Finally, perhaps, everything collapses back to a singularity. All the matter, all the energy, all the space-time of the universe compressed to a single point of infinite density and temperature. The same condition that, according to the Big Bang model, the universe emerged from 13.8 billion years ago, a point where physics as we understand it breaks down completely. What happens to light in this scenario is easier to answer than in the Big Rip. The photons persist throughout the contraction. Their energies increase. They become concentrated in ever smaller volumes of space. In the final moments, all the light that ever existed is compressed back to the singular point where the universe began. Energy is not destroyed. It is merely concentrated to an incomprehensible degree in an infinitely small space. Whether photons remain photons in that final singularity is unclear. At the energies and densities involved, the distinction between different types of particles becomes meaningless. Everything is converted to its most fundamental quantum state. Light and matter become indistinguishable. Some theories suggest that the Big Crunch is not truly an ending, but a transition. The fourth scenario, the Big Bounce. The universe contracts to a point, or nearly a point, and then rebounds. The crunch becomes a new bang. A new expansion begins. The cycle repeats, perhaps eternally. In this cyclic cosmology, the universe has no beginning and no ending, only an infinite series of expansions and contractions. Each cycle might last hundreds of billions of years. The universe expands, cools, forms galaxies and stars, evolves complexity, then contracts, heats up, destroys all structure, and bounces back into a new expansion phase. What happens to light in a bouncing universe? During expansion and contraction, it behaves as described in the Big Crunch scenario. But at the bounce point, something remarkable might happen. If information somehow survives through the bounce, if quantum states persist from one cycle to the next, then photons from the previous universe might influence the new universe. The light from the previous cycle, compressed and transformed at the bounce, might seed the initial conditions of the next cycle. This is highly speculative. We do not know if information can survive a bounce. We do not know if bounces are even possible or if they violate fundamental principles of thermodynamics. The second law presents a problem for cyclic universes. If entropy increases each cycle, eventually the universe must reach a maximum entropy state that cannot bounce. The cycles must end. Unless some mechanism resets entropy at each bounce, which would require physics beyond our current understanding. These four scenarios, heat death, Big Rip, Big Crunch, and Big Bounce, represent the main possibilities according to current physics. Each follows from general relativity and thermodynamics under different assumptions about the universe's content and the behavior of dark energy. Each offers a different fate for light. Which one is correct? Current observations favor heat death. The universe appears to be expanding at an accelerating rate driven by dark energy that behaves as a cosmological constant. If this continues, the universe will expand forever, cool forever, and eventually reach a maximum entropy state. Heat death seems most likely, but we could be wrong. Dark energy remains mysterious. We do not understand its nature or its source. Our observations cover only a brief moment in cosmic history. Extrapolating trillions of years into the future based on a few decades of data is inherently uncertain. What we can say with confidence is this: light's ultimate fate depends on the universe's ultimate fate. And the universe's ultimate fate remains an open question, one that observations in the coming decades might help answer more definitively. For now, let us proceed assuming heat death is correct, because it is most consistent with observations and because it offers the richest, strangest answer to our question about light's final destination. An answer that involves not destruction but transformation, not an ending but a fading. A gradual, inexorable decline into a state so cold and dark and dilute that light becomes indistinguishable from the quantum vacuum itself. To understand how this happens, we must follow the timeline in detail. We must track what happens to light as the universe ages through phases measured in timescales that dwarf all human experience. We must watch as stars die, black holes evaporate, and photons stretch into irrelevance. The journey continues into the deep future, into eras that have names but no witnesses, into a darkness so complete that the word darkness itself loses meaning. The universe, in the heat-death scenario, does not end suddenly. It fades, slowly, inevitably, across timescales so vast that human language struggles to describe them. Cosmologists have divided this long decline into distinct eras, each characterized by the dominant forms of matter and energy that shaped the cosmos during that time. We live in the stelliferous era, the age of stars. The brief, bright period when stellar fusion generates light and heat and drives the cosmic drama. But this era is temporary, a flash in the cosmic timeline. Stars have been shining for roughly 10 billion years. They will continue shining for perhaps 100 trillion years more. That sounds like forever. It is not. When the stelliferous era ends, when the last star burns out and darkness falls across the universe, new eras begin. Eras with less light, less energy, less happening. The cosmos enters a long, slow decline toward its final state. And light's story changes with each phase. Let us follow that story chronologically. Let us watch what happens to photons as the universe ages through each era, tracking their journey from the abundant present to the depleted far future. The timeline is almost incomprehensible in scope, but understanding it reveals exactly where light goes when everything else ends. We begin in the present, roughly 13.8 billion years after the Big Bang. The stelliferous era in full bloom. Stars fill the night sky. Galaxies shine across the cosmic web. Light floods space from countless sources. Every wavelength of the electromagnetic spectrum carries information. The universe glows with activity. New stars form constantly in our galaxy and in galaxies across the universe. Though star formation has slowed compared to the early universe, when galaxies first assembled and stars ignited in vast numbers, the process continues. Gas clouds collapse. Temperatures and pressures rise. Fusion ignites. New suns are born. These new stars will burn for millions or billions of years depending on their mass. Massive stars burn hot and fast, exhausting their fuel in mere millions of years. They die in supernova explosions, briefly outshining entire galaxies, scattering heavy elements into space, and leaving behind neutron stars or black holes. Smaller stars burn cool and slow, hoarding their hydrogen carefully, shining for trillions of years before finally exhausting their fuel. Each star, regardless of its mass or lifetime, is a photon factory. The fusion reactions in stellar cores release energy that works its way outward through the star's layers, eventually escaping as light. A single star like our Sun releases roughly 10 to the power of 45 photons every second. That is a 1 followed by 45 zeros. Every second, these photons stream into space carrying energy, information, and ultimately the fate of the stellar fuel that created them. Most photons travel until they are absorbed. They strike dust grains in interstellar space, heating them slightly. They fall into gas clouds, ionizing atoms, and driving chemistry. They reach planets, warming surfaces, and driving weather. A tiny fraction reach Earth, where some enter eyes and enable vision, others strike solar panels and generate electricity, others are absorbed by plants and power photosynthesis. Each photon's energy transfers to whatever absorbs it, converted from light into heat or chemical energy or electrical current. This is the current cosmic cycle. Stars create light. Matter absorbs it. The energy flows from hot stellar cores to cooler surroundings. Entropy increases. The second law is satisfied. The universe inches toward equilibrium, but very slowly, because new stars keep forming and new energy sources keep appearing. But the raw material for star formation is finite. Hydrogen fuel is abundant but not infinite. With every star that forms and burns, the supply dwindles. Most hydrogen in the universe exists in intergalactic space, too diffuse to collapse and form stars. The hydrogen locked in galaxies, where densities allow collapse, represents the accessible supply. And that supply has limits. Current estimates suggest that star formation will continue for roughly 100 trillion years. The number is not precise. It depends on uncertain factors like how efficiently gas cools and collapses, how much hydrogen is locked in compact objects or ejected from galaxies by supernova winds. But the order of magnitude is probably correct. Within roughly 10 to the power of 14 years from now, star formation ceases. The final stars to form will be red dwarfs, the smallest stars capable of sustaining fusion. If information somehow survives through the bounce, if quantum states persist from one cycle to the next, then photons from the previous universe might influence the new universe. The light from the previous cycle, compressed and transformed at the bounce, might seed the initial conditions of the next cycle. This is highly speculative. We do not know if information can survive a bounce. We do not know if bounces are even possible or if they violate fundamental principles of thermodynamics. The second law presents a problem for cyclic universes. If entropy increases each cycle, eventually the universe must reach a maximum entropy state that cannot bounce. The cycles must end, unless some mechanism resets entropy at each bounce, which would require physics beyond our current understanding. These four scenarios, heat death, big rip, big crunch, and big bounce, represent the main possibilities according to current physics. Each follows from general relativity and thermodynamics under different assumptions about the universe's content and the behavior of dark energy. Each offers a different fate for light. Which one is correct? Current observations favor heat death. The universe appears to be expanding at an accelerating rate driven by dark energy that behaves as a cosmological constant. If this continues, the universe will expand forever, cool forever, and eventually reach a maximum entropy state. Heat death seems most likely, but we could be wrong. Dark energy remains mysterious. We do not understand its nature or its source. Our observations cover only a brief moment in cosmic history. Extrapolating trillions of years into the future based on a few decades of data is inherently uncertain. What we can say with confidence is this: light's ultimate fate depends on the universe's ultimate fate. When the final fusion photon escapes from the final dying star, a threshold is crossed. The primary source of new photons in the universe has shut off. Stars no longer create light. The stelliferous era has ended. The universe enters the degenerate era. This name refers to the quantum mechanical state of the matter that dominates this epoch. Stars have become stellar remnants: white dwarfs, neutron stars, and black holes. These are degenerate objects, held up against gravity not by thermal pressure, but by quantum mechanical pressure arising from the Pauli exclusion principle. Electrons, or neutrons, or even more exotic particles are packed so tightly that quantum mechanics forbids them from occupying the same state, creating an outward pressure that balances gravity. The degenerate era begins around 10 to the power of 14 years from now and lasts until approximately 10 to the power of 40 years. During this immense span of time, white dwarfs and neutron stars cool slowly, radiating away their residual heat. They start hot, heated by the leftover thermal energy from their stellar past. But with no fusion to replenish heat, they must radiate it away to space. A white dwarf, freshly formed from the death of a sun, like star, has a surface temperature of perhaps 100,000 Kelvin. It glows white, hot, though it generates no energy internally. It is simply cooling, like an ember removed from a fire. Over billions of years, it cools to 10,000 Kelvin, then 1,000 Kelvin, eventually approaching the temperature of the cosmic microwave background itself. As it cools, the photons it emits shift to longer wavelengths. Initially, it radiates ultraviolet and visible light, then infrared, then microwave radiation. Eventually, when its temperature drops below a few Kelvin, it barely radiates at all. It becomes a black dwarf, a cold, dark sphere of carbon and oxygen, invisible against the darkness of space. This cooling process takes an extraordinarily long time. Current estimates suggest that white dwarfs might take 10 to the power of 20 years or longer to cool to the temperature of the cosmic background. During all that time, they emit photons, fewer and fewer as they cool, lower and lower energy as their temperature drops. But they contribute to the cosmic photon inventory, replacing at least some of the stellar photons that are no longer being created. Neutron stars follow a similar cooling trajectory, though their physics is more complex. Their surfaces initially radiate X rays and gamma rays, photons with energies far higher than visible light. They cool more quickly than white dwarfs in some respects because their small surface area radiates energy less efficiently and because exotic cooling processes involving neutrino emission drain heat from their interiors. But they too eventually fade to invisibility, becoming cold neutron spheres drifting through space. During the degenerate era, these cooling stellar remnants represent the primary sources of new photons. But they are far less luminous than active stars. They do not create energy through fusion. They simply radiate away the thermal energy they inherited from their past. This is a one-time expenditure, not a renewable resource. Once the heat is gone, it is gone. The photons produced during this era are predominantly low energy, infrared and microwave photons, not visible light. An observer in the degenerate era would see a universe darker than anything visible today. No stars shine. Stellar remnants glow dimly in infrared if they are warm enough, but most have cooled beyond detectability. The cosmic microwave background has cooled as well, shifted by continued expansion to even longer wavelengths and lower temperatures. The universe is dark and cold, though not yet completely dark or completely cold. Black holes complicate the picture. They do not cool in the conventional sense because they do not emit thermal radiation in the conventional sense. Or rather, they do, but through a quantum mechanical process so slow and strange that it barely matters for black holes of stellar mass or larger. In 1974, Stephen Hawking discovered something remarkable. Black holes are not perfectly black. They emit radiation, not from inside the event horizon, but from quantum effects just outside it. The vacuum of space is not truly empty. It seethes with virtual particles that pop into existence in particle-antiparticle pairs and immediately annihilate. Normally, these pairs exist for such a brief time that they have no measurable effect. But near a black hole's event horizon, something strange can happen. If a particle-antiparticle pair appears just outside the horizon, one member might fall in while the other escapes. To an outside observer, it appears that the black hole has emitted a particle. This is Hawking radiation, and it carries energy. That energy must come from somewhere. It comes from the black hole's mass. The black hole slowly evaporates. For stellar mass black holes, the Hawking radiation is negligible during the degenerate era. The temperature of Hawking radiation is inversely proportional to the black hole's mass. A solar mass black hole has a Hawking temperature of roughly 1/10 millionth of a Kelvin, far colder than the cosmic microwave background. Such a black hole actually absorbs more energy from the background than it emits. It grows very slowly as it absorbs photons from space. Only after the universe expands and cools sufficiently does Hawking radiation become relevant for stellar mass black holes. The cosmic microwave background must cool below the Hawking temperature. This happens during the later stages of the degenerate era. This happens after the universe has expanded for timescales approaching 10 to the power of 20 years or more. Once the background temperature drops below the Hawking temperature, black holes begin to lose mass through radiation. Slowly at first, incredibly slowly. A solar mass black hole loses mass through Hawking radiation at a rate of roughly 10 to the power of -17 kilograms per second. At this rate, complete evaporation takes 10 to the power of 67 years. Larger black holes evaporate even more slowly. A million solar mass black hole takes 10 to the power of 79 years. A billion solar mass black hole takes 10 to the power of 91 years. The supermassive black holes at the centers of galaxies, with masses of billions of solar masses, require timescales approaching 10 to the power of 100 years to evaporate completely. These numbers defy comprehension. 10 to the power of 100 is called a googol. It is vastly larger than the number of atoms in the observable universe. It exceeds the number of Planck times that have elapsed since the Big Bang by a factor so large that it has no intuitive meaning. Yet this is the timescale required for the largest black holes to evaporate. But time, in this scenario, is unlimited. The universe continues expanding. The temperature continues dropping. And eventually, inevitably, even the largest black holes complete their evaporation. When they do, they release their mass, energy back into the universe as radiation. A spray of photons and particles, the last gasp of gravitational collapse, radiating away the concentrated energy that the black hole held for eons. The evaporation of black holes marks the transition to the next era. The black hole era, from roughly 10 to the power of 40 years to 10 to the power of 100 years. During this time, black holes are the dominant form of matter in the universe. White dwarfs have long since cooled to black dwarfs. Neutron stars have cooled to invisibility. Planets and asteroids and all the debris of the stellar era have either fallen into black holes or been ejected from galaxies and scattered into the cosmic void. What remains are black holes of various masses, slowly evaporating through Hawking radiation, and a thin gas of particles that avoided capture. This gas includes photons from earlier eras, their wavelengths stretched by expansion to enormous lengths and incredibly low energies. It includes neutrinos, lightweight particles that barely interact with anything and have been traveling unhindered since the early universe. It includes stray protons and electrons, leftovers from dead stars and evaporated planets, drifting through space with no destination. During the black hole era, very little happens. The universe is dark. The temperature is within a tiny fraction of absolute zero. Space is almost empty. Occasionally, a black hole evaporates, releasing a burst of Hawking radiation, the intensity of which increases as the black hole shrinks. The final moments of black hole evaporation are relatively dramatic. A small black hole radiates intensely in its last seconds, releasing its remaining mass, energy in a flash of high-energy photons. But these flashes are rare and scattered across cosmic distances. Most of space-time is utterly dark and quiet. No stars shine. No fusion occurs. No chemistry happens. The universe has become a thin, cold, dilute gas of particles expanding into an ever larger volume. The distance between any two particles increasing constantly as space stretches. And light. Where is light in this era? Light exists, but transformed beyond recognition. The photons born in the stelliferous era have been traveling and redshifting for timescales measured in googolls of years. Their wavelengths have stretched to scales larger than galaxies. Their energies have diminished to levels approaching zero. They are technically photons, but they carry so little energy and are spread so thin that they have become indistinguishable from the quantum noise of the vacuum itself. The photons from Hawking radiation, the bursts emitted when black holes evaporate, are newer. They have not had as much time to redshift, but they too are diluted by the vast expansion of space. The universe is so large by this point that even a tremendous flash of Hawking radiation from an evaporating black hole becomes undetectable within a relatively short time. Its photons scattered across volumes of space, so immense that the probability of any two photons ever interacting again approaches zero. When the last black hole evaporates, perhaps 10 to the power of 100 years from now, perhaps longer if some supermassive black holes exceed current mass estimates, the black hole era ends. The universe transitions to its final state. The dark era. Maximum entropy. Heat death. What does the dark era look like? Imagine a universe expanded to such an immense size that the distance between any two particles is larger than the current observable universe. Imagine a temperature so close to absolute zero that quantum mechanics barely allows any energy to exist. Imagine a photon so stretched that its wavelength exceeds the size of galactic superclusters, and its energy is smaller than any conceivable measurement could detect. This is heat death, not a state where nothing exists. Energy conservation forbids the destruction of energy. The photons still exist. The particles still exist. But they are spread so thin, so cold, so depleted of any useful energy, that nothing can happen. No processes can occur. No events can unfold. Time, in a practical sense, stops having meaning. The second law of thermodynamics has won its final victory. Entropy has reached its maximum. Every temperature gradient has flattened. Every energy source has exhausted itself. The universe has explored every possible arrangement of its particles and settled into the vast sea of maximum entropy configurations. No further change is possible that would increase entropy. And because entropy cannot decrease, no change is possible at all. Light, in this final state, has not disappeared, but it has transformed into something so diffuse and low energy that calling it light seems almost wrong. The photons exist as excitations of the electromagnetic field, quantum states with wavelengths approaching infinity and energies approaching zero. They satisfy the mathematical definition of photons, but they bear no resemblance to the light we experience in everyday life or even to the cosmic microwave background of the current era. An observer in the dark era, if such an observer could exist, would detect no light. Not because light is absent, but because the photons carry so little energy and are separated by such vast distances that no detector, no matter how sensitive, could register them. The universe appears completely dark because it effectively is completely dark. The photons are there, but they are invisible, unreachable, impossible to collect or concentrate or use for any purpose. This is where light goes when the universe ends in heat death, not into oblivion, not into destruction, into a state of maximum dilution and minimum energy, spread across infinite space, cooled to infinitesimal temperature, transformed from the bright photons that once carried information about stars and galaxies into phantom excitations of a quantum field that might as well not exist. But this raises a question that physics has not fully answered. Can photons truly reach zero energy? Or does quantum mechanics impose some limit, some floor below which energy cannot fall? The question touches on deep issues in quantum field theory and cosmology. In flat spacetime, photons can have arbitrarily low energy. There is no theoretical minimum. A photon's energy is determined by its wavelength, and wavelengths can be arbitrarily long. As the universe expands, photon wavelengths stretch without limit, and energies approach zero without ever quite reaching it. However, quantum mechanics introduces uncertainty. The energy of a quantum system cannot be known with perfect precision. There are fluctuations, uncertainties governed by the Heisenberg uncertainty principle. Even in a state of minimum energy, quantum fields experience zero-point fluctuations, tiny variations in energy that arise from fundamental quantum uncertainty. These zero-point fluctuations mean that the vacuum is not truly empty. It seethes with virtual particles, temporary excitations that pop into existence and disappear on timescales governed by the uncertainty principle. In a sense, the vacuum has energy even when it contains no real particles. As photons redshift to lower and lower energies, they approach the energy scale of vacuum fluctuations. When a photon's energy becomes comparable to the uncertainty in the vacuum energy, the distinction between a real photon and a vacuum fluctuation blurs. The photon becomes indistinguishable from the quantum noise of the vacuum itself. This does not mean the photon has been destroyed. Energy is still conserved. The photon still exists as a quantum state, but it has become so dilute, so low energy, so mixed with vacuum fluctuations that it cannot be meaningfully separated from the background noise of quantum fields. In this sense, light's ultimate fate in heat death is not annihilation but dissolution. Photons dissolve into the quantum vacuum, becoming part of the fundamental uncertainty that permeates all of space. They lose their identity as distinct particles. They merge with the background. They become undetectable, unusable, effectively gone even though technically still present. This is as close to true death as light can experience. Not destruction, because energy cannot be destroyed, but a transformation so complete that the photon ceases to have any physical significance. It exists mathematically, but not practically. It satisfies conservation laws, but not measurability conditions. It is and is not simultaneously, in a way that defies everyday intuition but makes perfect sense in the strange world of quantum mechanics. And this fate is not just for the photons born near the end. It is the fate of all photons, the light from the first stars, the cosmic microwave background, every photon ever emitted by every star that ever burned, all redshifted, diluted, cooled, expanded to wavelengths larger than the observable universe, and energy smaller than any conceivable detector could measure. The universe in heat death contains all the light that ever existed. But that light has been transformed beyond recognition, stretched and cooled and diluted until it becomes indistinguishable from nothing at all. This is the answer to where light goes when the universe ends. If heat death is correct, light goes nowhere. It remains in the universe, conserved by fundamental laws, but transformed into a state so diffuse and depleted that it effectively ceases to exist as light. The photons are still there, formally, mathematically, but they are invisible, unreachable, dissolved into the quantum foam of an expanding vacuum approaching absolute zero. The journey of every photon ends not with a bang, but with an asymptotic approach to nothingness. Not destruction, but dissipation. Not annihilation, but dilution. A slow fade into the quantum background noise of an infinitely expanding, infinitely cooling, infinitely darkening cosmos. And in this final state, the universe becomes timeless in a peculiar way. With no energy gradients to drive processes, with no events unfolding to mark the passage of time, with no change occurring that would distinguish one moment from the next, time loses its physical meaning. The arrow of time, which points from low entropy to high entropy, reaches the end of its trajectory. Entropy has maximized. The arrow has nowhere left to point. An observer, if one could exist, would experience an eternal now. No past different from the present. No future different from now. Just an unchanging state that persists forever because nothing remains that could cause it to change. This is the true death of the universe. Not a final explosion or collapse, but a final stillness. A state of maximum entropy from which no escape is possible and in which no events can occur. And light, which once connected distant stars and carried information across the cosmos, has become nothing more than imperceptible ripples in the fabric of an empty, cold, dark, timeless void. But our story is not quite finished. We have followed heat death to its conclusion. But what about the other scenarios? What happens to light in the big rip, the big crunch, the big bounce? Each offers a different fate, and exploring them reveals different aspects of what light truly is and how it responds to the most extreme conditions imaginable. Death is perhaps the wrong word for what happens to light. Death implies cessation, an ending, a transition from existence to non-existence. But light does not die in that sense. It cannot. Energy conservation, one of the most fundamental laws in physics, forbids the destruction of energy. A photon is pure energy. It cannot simply vanish. Yet something happens to light in the heat-death scenario that is difficult to describe without using words like death or ending. The photons persist, yes, but transform so completely that they lose all the properties we associate with light. They become undetectable, unusable, indistinguishable from vacuum. This transformation deserves careful examination because it reveals something profound about what light actually is and what happens when the universe reaches maximum entropy. Let us start with what we know for certain. A photon carries energy. The relationship between energy and wavelength is exact. Energy equals Planck's constant times the speed of light divided by wavelength. This means that as wavelength increases, energy decreases. Double the wavelength, have the energy. Stretch the wavelength to infinity, and energy approaches zero. In an expanding universe, photon wavelengths stretch with the expansion of space. This is not like a photon moving through space and somehow getting tired. The photon is not losing energy to friction or resistance. Space itself is expanding, carrying the photon along, stretching its wavelength as it goes. The expansion happens everywhere simultaneously, so every photon experiences this stretching regardless of where it is or where it is going. The cosmic microwave background provides a perfect example. These photons were emitted roughly 380,000 years after the Big Bang, when the universe cooled enough for atoms to form. At that time, they were primarily visible and infrared photons, corresponding to a temperature of roughly 3,000 Kelvin. Since then, the universe has expanded by a factor of roughly 1,100. The wavelengths of these photons have stretched by the same factor. What were visible photons with wavelengths around 500 nanometers are now microwave photons with wavelengths around 0.5 millimeters. The energy has decreased by a factor of 1,100. This stretching continues. Right now, as the universe expands, the cosmic microwave background is cooling. Its temperature, currently about 2.7 Kelvin, drops continuously as expansion stretches the photons to longer wavelengths. In another trillion years, the temperature will have dropped to perhaps 0.1 Kelvin or less. In 10 to the power of 20 years, it will be measured in microkelvins. In 10 to the power of 100 years, it will be within an infinitesimal fraction of absolute zero. But here is the key question. Can it reach absolute zero? Can the temperature drop all the way to zero? Can photon energy reach exactly zero? Thermodynamics says no. The third law of thermodynamics states that absolute zero cannot be reached in a finite number of steps. You can get arbitrarily close, but never quite there. Every cooling process leaves you with some residual energy, some minimum temperature above zero. But the third law applies to systems reaching thermal equilibrium through finite processes. The heat death scenario involves infinite time and infinite expansion. Does the third law still apply? Or can photon energies asymptotically approach zero without ever quite reaching it, getting closer and closer forever without hitting the limit? The answer depends on subtle issues in quantum field theory and general relativity that physics has not fully resolved. In flat spacetime, a photon can have arbitrarily low energy. There is no minimum. But in expanding curved spacetime, the situation is less clear. The expansion of space is a global property that affects all wavelengths simultaneously. As expansion continues toward infinity, photon energies approach zero from above but may never actually reach it. What matters practically is that photons become so low in energy that they cannot participate in any physical process. Quantum mechanics imposes a floor on detectability. Any measurement device has a finite energy resolution. Any detector must interact with a photon to detect it, and that interaction requires some minimum energy transfer. When photons are so stretched and so depleted that their energy falls below any conceivable detector's sensitivity, they become effectively undetectable. This is not just a technological limitation. It is a fundamental physical limit arising from quantum mechanics. The uncertainty principle relates energy and time. The uncertainty in energy times the uncertainty in time must exceed Planck's constant divided by 2. To measure a very low energy photon with perfect precision, you would need an infinite amount of time. In practice, measurements take finite time, so very low energy photons cannot be distinguished from quantum vacuum fluctuations. Vacuum fluctuations are a fundamental feature of quantum fields. Even in the absence of any particles, quantum fields fluctuate. Virtual particle-antiparticle pairs pop into existence and annihilate constantly, existing for time spans governed by the uncertainty principle. These fluctuations represent the irreducible quantum noise of empty space. The energy scale of vacuum fluctuations depends on the region of space considered and the timescale over which measurements occur. But generally, when a photon's energy becomes comparable to the energy uncertainty of vacuum fluctuations, the photon can no longer be meaningfully distinguished from the vacuum. It merges with the background noise. This is what happens to light in the extreme expansion of heat death. Photons are stretched to such low energies that they become indistinguishable from vacuum fluctuations. They still exist as quantum states of the electromagnetic field. They still carry energy, technically, but they are mixed into the quantum foam of space-time, impossible to separate from the fluctuations that exist even in perfect vacuum. In a sense, the photons dissolve into the vacuum. They do not disappear. They do not violate conservation laws. They simply become part of the fundamental quantum uncertainty that permeates all of space. The distinction between photon and vacuum fluctuation becomes meaningless when energies are low enough and expansion is large enough. This dissolution is light's ultimate fate in heat death. Not destruction, but indistinguishability. The photon exists but cannot be found. It carries energy but cannot transfer it. It propagates through space but cannot be detected. It satisfies the equations of quantum electrodynamics perfectly but has no observable consequences. Now consider what this means for information. Light carries information. The wavelength, direction, polarization, and phase of a photon encode data about its source and its history. When you see a star, the photons entering your eye carry information about the star's temperature, composition, motion, and distance. This information is physical. It has consequences. It can be measured and used. But information, like energy, follows conservation principles. In quantum mechanics, information cannot be destroyed. This principle underlies many arguments in theoretical physics, including the black hole information paradox. If information cannot be destroyed, what happens to the information carried by photons in heat death? The photons still exist, so formally the information still exists, but it has been encrypted in a way that makes it practically unrecoverable. The photons are so diluted and so low in energy that measuring them would require collecting an impossible number of them across an impossible volume of space. The information is preserved in principle but lost in practice. This is similar to what happens when you burn a book. The information in the book is not destroyed. It is converted to heat, smoke, and ash. In principle, if you knew the exact quantum state of every particle in the smoke and ash and scattered photons, you could reconstruct the book. But in practice, the information is scrambled beyond any realistic hope of recovery. It exists but is inaccessible. Photons in heat death suffer a similar fate. The information they carry about their sources, their histories, their journeys across cosmic time is preserved in the quantum states of electromagnetic field excitations spread across infinite space. But recovering that information would require measurements of such precision and scope that they are prohibited by the laws of physics themselves. In this sense, the information death of light mirrors its energy death, not destroyed, but rendered inaccessible, not annihilated, but scrambled beyond recovery. The photon exists, the information exists, but both have entered a state where they cannot be used for anything. This raises a philosophical question. If a photon exists but cannot be detected, if it carries energy but cannot transfer it, in what sense does it exist? Is existence purely a matter of satisfying mathematical equations? Or does existence require some form of measurability, some potential to affect other things? Quantum mechanics does not provide a clear answer. In quantum field theory, particles are excitations of fields that permeate all of space. A photon is an excitation of the electromagnetic field. As long as the field exists and supports the excitation, the photon exists, regardless of whether anything can detect it. But fields are mathematical objects. They are tools we use to describe physical reality, not reality itself. Or are they? This question touches on the nature of reality itself, on what it means for something to exist when it cannot be observed or measured or interacted with. In the heat death scenario, these questions become more than philosophical. They become practical descriptions of the universe's final state. A universe filled with undetectable photons, carrying energy that cannot be used, encoding information that cannot be read, propagating through an expanding void toward no destination. Now let us consider the role of time. Time and entropy are intimately connected. The arrow of time, the fact that we experience time flowing from past to future and not the reverse, arises from the second law of thermodynamics. Entropy increases. Systems evolve from ordered to disordered states. This provides an arrow, a direction, a way to distinguish past from future even in the equations of physics, which are mostly time, reversible. In the early universe, entropy was low. The Big Bang created a highly ordered state with all energy and matter concentrated in a small volume. As the universe expanded and cooled, entropy increased. Stars formed, burned, and died. Galaxies assembled and evolved. Complexity arose and then dissipated. Each step increased total entropy. The arrow of time pointed from the ordered Big Bang toward increasingly disordered future states. Heat death represents maximum entropy. The arrow of time has reached its target. No further increase is possible. And without increasing entropy, there is no way to distinguish past from future. Time, in a physical sense, stops having meaning. This does not mean time ceases to exist. Clocks, if they could exist in heat death, would still tick. Particles would still move. Photons would still propagate. But nothing would change in any meaningful way. The universe would be in the same maximum entropy state at all times. No events would occur that could mark the passage of time. No memories could form because forming memories requires creating lower entropy information structures, which is impossible when entropy is already maximal. An observer in heat death, if such a thing could exist, would experience an eternal now. No past different from the present. No future different from now. An unchanging state persisting forever. Time would flow, in some abstract sense, but without any physical consequences. The clock ticks would be meaningless because nothing changes between ticks. Light participates in this timelessness. Photons continue to propagate, but their propagation accomplishes nothing. They travel from nowhere to nowhere through a universe that looks the same everywhere. Their speed, still the cosmic speed limit, determines nothing because no information is being transmitted and no events are being connected. Light moves at the speed of light through a universe where motion has ceased to matter. This is perhaps the strangest aspect of light's fate in heat death. The photons persist. They move. They satisfy Einstein's equations. They propagate at exactly 299,792,458 meters per second through the vacuum. But their motion is pointless. They are running in place in a universe that has stopped running. There is a deep irony here. Light, the fastest thing in the universe, the phenomenon that sets the cosmic speed limit and connects distant events through causality, ends its journey moving at maximum speed through a universe where nothing is happening. The fastest thing accomplishes nothing because there is nothing left to accomplish. Now consider what heat death means for the concept of observation. Quantum mechanics assigns a special role to observation. The act of measurement affects quantum systems, collapsing superpositions, determining outcomes, creating definite states from probabilistic potentials. But observation requires an observer, and observers require low entropy systems capable of recording information. In heat death, no observers exist. Nothing exists that could count as a measuring device. The universe is at maximum entropy, which means no structure can exist that could observe or record or remember anything. Quantum mechanics suggests that without observers, quantum states remain in superposition. Probabilities never collapse into definite outcomes. What does this mean for photons? A photon exists in a superposition of all possible paths until it is observed. In heat death, with no observers, do all photons remain in superposition forever? Do they exist in a quantum fog of all possible states simultaneously, never collapsing into definite realities because nothing can measure them? This is speculative. Quantum mechanics was developed to describe systems that can be observed and measured. Extending it to a universe with no observers requires interpretations that go beyond established physics. But it suggests that light and heat death might exist in a strange quantum limbo, neither definitely here nor there, neither definitely this wavelength nor that, spread across all possible states without anything to collapse the wave function and make those states definite. If this is correct, then light's final transformation is not just from high energy to low energy, not just from detectable to undetectable, but from classical reality to pure quantum potential. Photons dissolve not just into the vacuum, but into the space of all possible photon states, existing in perfect superposition because nothing remains that could observe them and force them into definite existence. This is speculative, yes, but it follows logically from taking quantum mechanics seriously in the context of heat death. And it suggests that light's ultimate fate is stranger than simple dilution and cooling. It is a transformation from definite particle to indefinite quantum possibility, from thing to abstraction, from reality to mathematics. But we are not done exploring light as possible fates. Heat death is only one scenario. The universe might end differently, and different endings offer different transformations for light. Some more violent, some more final, some that preserve light in unexpected ways. Let us turn now to those other scenarios and see what they reveal about the ultimate nature of photons, energy, and existence itself. Heat death offers one answer to where light goes. But the universe might not end that way. Dark energy might behave differently than we currently observe. The fundamental parameters of cosmology might shift. And if they do, light faces entirely different fates. Some more dramatic than the slow fade of heat death. Some that preserve light in unexpected forms. Some that destroy it utterly. Let us explore these alternatives systematically, following light through each possible ending and seeing what physics reveals about its ultimate transformation. The Big Rip represents the most violent ending imaginable. It occurs if dark energy, instead of remaining constant, grows stronger over time. Currently, dark energy appears to maintain a constant density even as the universe expands. This seems paradoxical. As space expands, matter becomes more dilute. Its density drops, but dark energy does not dilute. Each cubic meter of expanding space contains the same amount of dark energy as before. Where does this energy come from? The expansion itself creates it, in a process that sounds like it violates energy conservation but actually does not, due to subtle issues in how energy is defined in general relativity. If dark energy maintains constant density as space expands, the total amount of dark energy in the universe increases as the volume of space increases. This drives accelerating expansion. The more space expands, the more dark energy exists, the faster expansion accelerates. This feedback loop continues indefinitely, but the acceleration remains bounded. It grows, but does not become infinite. The Big Rip scenario assumes dark energy behaves differently. Instead of maintaining constant density, it grows denser, or its repulsive effect intensifies. The equations that describe this use a parameter called the equation of state, symbolized by the letter W. For a cosmological constant, W equals -1 exactly. For a Big Rip to occur, W must be less than -1. Dark energy must be phantom energy that violates certain classical energy conditions. Current observations constrain WES to be very close to -1, but the error bars leave room for phantom energy. We cannot rule out W less than -1 with certainty. And if W is even slightly less than -1, if dark energy is phantom energy, the universe faces a violent end. The progression toward this end is systematic. First, the acceleration of expansion increases. Galaxy clusters that are currently bound by gravity, destined to remain together for trillions of years in the heat death scenario, are torn apart. The galaxies within these clusters separate, driven apart by expansion that overcomes their mutual gravitational attraction. The night sky slowly empties as distant galaxies recede beyond the cosmic horizon. But expansion does not stop accelerating. It continues to strengthen. Eventually, it becomes powerful enough to unbind individual galaxies. The Milky Way, if it still exists when this happens, is pulled apart. Stars at its edges are ripped away first, then stars throughout the galactic disk. Finally, even stars near the galactic center, where gravity is strongest, are separated from each other. The galaxy dissolves into billions of isolated stars scattered across expanding space. Still, the acceleration grows. It becomes strong enough to unbind solar systems. Planets are torn from their orbits around stars. Moons are separated from planets. The Earth and Moon, bound together for billions of years, are ripped apart. The Earth and Sun, held in orbital relationship since the solar system's formation, separate. Every gravitationally bound system in the universe dissolves. The process continues down to smaller scales. Objects held together by weaker forces unbind before objects held by stronger forces. Eventually, expansion becomes strong enough to overcome the electromagnetic forces holding molecules together. Chemical bonds break. DNA unravels. Proteins denature. Cells are torn apart at the molecular level. Every chemical structure in the universe dissolves. Then atomic structure fails. The electromagnetic force binding electrons to atomic nuclei is overcome by expansion. Electrons are ripped away from atoms. Matter becomes a plasma of free electrons and nuclei. This is not heat, induced ionization, where thermal energy overcomes binding energy. This is space itself expanding so rapidly that the distance between electron and nucleus increases faster than electromagnetic force can maintain the bond. Finally, in the last moments before the end, even nuclear forces fail. The strong force, which binds protons and neutrons into atomic nuclei, is the strongest force in physics. But against exponentially accelerating expansion, even the strong force cannot hold. Nuclei are torn apart into free protons and neutrons. Then protons and neutrons themselves are ripped into their constituent quarks. The fundamental particles that compose matter are shredded. This cascade from galaxy clusters to quarks might take millions or billions of years, depending on how quickly dark energy strengthens. But the endpoint is always the same. A singularity called the Big Rip, where expansion rate becomes infinite, space-time itself tears apart, and the universe as we understand it ceases to exist. What happens to light during this process? For most of the Big Rip timeline, photons behave normally. They travel through expanding space. Their wavelengths stretch due to expansion. Their energies decrease due to redshift. The accelerating expansion makes this cooling more rapid than in the heat-death scenario, but the basic physics remains the same. Photons are created by various processes. They propagate through space. Some are absorbed. Others continue traveling, gradually losing energy to expansion. As objects are torn apart, some of those disruptions release energy, potentially creating new photons. When galaxies are torn apart, the violent gravitational interactions might heat gas and produce radiation. When stars are separated from each other, tidal forces might trigger nuclear reactions that generate light. When chemical bonds are broken, the released energy might appear as photons. Throughout the destruction, light is both destroyed through absorption and created through violent processes. But as the Big Rip approaches its climax, space-time itself becomes unstable. The fabric of space develops tears and discontinuities. General relativity, which describes space as a smooth manifold, breaks down. The notion of photons propagating smoothly through space becomes ill-defined when space itself is fragmenting. In the final moments, measured perhaps in seconds or microseconds before infinite expansion, photons experience the same tearing that affects everything else. Their wave functions, which depend on the underlying structure of space-time, are disrupted. The electromagnetic field that supports photon excitations becomes undefined when the space-time supporting the field disintegrates. What this means is unclear. Does the photon cease to exist when space-time tears apart? Does it transform into some other quantum state not describable by our current theories? Does the very question become meaningless when the arena of physics, space-time itself, no longer exists? We do not know. Physics has no framework for describing what happens when space-time itself is destroyed. General relativity assumes space-time is continuous and smooth. Quantum field theory assumes fields exist on a space-time background. When that background disintegrates, the theories have nothing to say. Perhaps quantum gravity, a theory that unifies general relativity and quantum mechanics, would provide answers. But quantum gravity remains incomplete. String theory, loop quantum gravity, and other approaches offer possibilities but no definitive predictions. The Big Rip, if it occurs, represents a regime where current physics fails completely. What we can say is this. In the Big Rip scenario, light does not gently fade like in heat death. It is violently destroyed when the space-time supporting it is torn apart. The photons that have traveled across cosmic distances for billions of years, carrying information about stars and galaxies, are shredded along with everything else. Information is lost, perhaps permanently, perhaps in a way that violates quantum mechanical principles. The ending is total and final. Now consider the opposite scenario. The The Big Crunch. Instead of expansion accelerating forever, it slows, stops, and reverses. The universe collapses back on itself. Everything that has been separating begins to approach. Galaxies move toward each other instead of apart. The cosmic microwave background, which has been cooling since the Big Bang, begins to heat up. This scenario requires that the universe contain enough matter and energy to overcome dark energy and halt expansion. Currently, observations suggest this is not the case. Dark energy dominates. Expansion accelerates. But if dark energy weakens or disappears, if its nature changes in ways we have not predicted, gravity might eventually win and pull everything back together. The Big Crunch mirrors the Big Bang in reverse. Galaxies collide and merge. Space contracts. The distance between objects decreases. And crucially for our question about light, the expansion that has been redshifting photons now reverses. Contraction blue shifts them. A photon traveling through contracting space experiences the opposite of redshift. Its wavelength compresses instead of stretches. Its energy increases instead of decreases. A photon that started as a microwave becomes infrared, then visible light, then ultraviolet, then X-ray, then gamma ray. Its energy grows without limit as contraction continues. The cosmic microwave background, currently at 2.7 Kelvin, heats up. In a contracting universe, it gains energy from the compression of space. Its temperature rises proportional to the inverse of the scale factor. As space shrinks by a factor of 2, temperature doubles. Shrink space by a factor of 1,000, temperature increases 1,000-fold. Eventually, the background radiation becomes so hot that it dominates everything else. The universe glows with intense light from all directions. No stars are visible because the background outshines them. Space becomes opaque as high. Energy photons scatter off matter constantly. The universe resembles the hot, dense plasma that existed shortly after the Big Bang, but now moving toward compression rather than emerging from it. All the light that ever existed, every photon emitted by every star that ever burned, is still present in this contracting universe. None have been destroyed. Energy conservation holds throughout, but they are all being compressed into smaller and smaller volumes, gaining energy from contraction, becoming more and more energetic. As the universe approaches the final singularity, photon energies approach infinity. Wavelengths approach zero. The electromagnetic field becomes increasingly energetic. At some point, photons become so energetic that they create particle-antiparticle pairs when they collide with each other. Matter and antimatter appear from pure light energy, then annihilate back into light. The universe becomes a roiling plasma where matter and energy constantly interconvert. Finally, everything collapses to a singularity. All matter, all energy, all space-time compressed to a single point of infinite density, infinite temperature, infinite curvature. This is a true singularity, a breakdown of physics, a state where general relativity predicts its own failure. What happens to light at the singularity? The photons are there, compressed along with everything else. Their energy has become infinite. Their wavelength has become zero. But these infinities signal the failure of the theory. Physics cannot describe what happens at a singularity because the equations produce undefined results. In some sense, all the light that ever existed is present at the singularity, concentrated to an infinitesimal point. The photons that traveled for billions of years across expanding space have been compressed back to the origin. Their journeys have been reversed. Their histories have been rewound to a single point where all photons, all matter, all space-time converge. Whether this represents an ending or a transition depends on what happens next. In the simple Big Crunch scenario, the singularity is the end. Time stops. Space ceases to exist. Everything, including light, reaches a final state beyond which physics cannot describe. But another possibility exists. The Big Bounce. The universe collapses to a singularity, or nearly a singularity, and then rebounds. The crunch becomes a new bang. Compression becomes expansion. The cycle repeats. In a bouncing cosmology, the The singularity is not truly singular. Something prevents complete collapse. Perhaps quantum gravitational effects become important at extremely high densities and halt the collapse. Perhaps the universe reaches a minimum size and then expands again due to quantum effects we do not yet understand. Various theories propose mechanisms for the bounce, but none are confirmed. If a bounce occurs, what happens to light? During the contraction phase, photons are compressed and energized as described. They reach extremely high energies as the universe approaches its minimum size. At the bounce point, the quantum state of the universe undergoes a transition. Contraction becomes expansion. As expansion begins, photons are redshifted again. They lose the energy they gained during contraction. The universe cools as it expands, just as it did after the original Big Bang. The photons spread out, their wavelengths stretch, their energies decrease. But here is the key question. Are these the same photons? Or are they new photons created by the bounce? Does information survive through the bounce, or is it erased? If information survives, then the photons in the new universe cycle carry imprints of the previous cycle. The quantum states of electromagnetic fields pass through the bounce and seed the initial conditions of the new expansion. In this sense, light from the previous universe influences the new universe, even though the photons themselves are transformed by the bounce. If information does not survive, then the bounce resets everything. The photons in the new cycle are truly new, created by the bounce process itself, carrying no memory of the previous universe. Light from the old universe is destroyed, or rather, dissolved into the quantum state that generates the new universe. Current physics cannot answer this question definitively. We do not have a complete theory of quantum gravity that describes bounces. We do not know if information can survive through such extreme conditions. Different approaches to quantum gravity give different answers. String theory suggests information is preserved in quantum transitions, which would imply that light from a previous cycle influences the next. Loop quantum gravity, which describes space as quantized at the smallest scales, allows bounces where information might or might not survive, depending on details of the model. We simply do not know. What we can say is this: in a bouncing universe, light does not reach a final state. It is transformed cyclically, compressed during contraction, expanded during expansion, possibly preserved through the bounce, possibly reset. The photons that exist now might be descendants of photons from a previous cycle, carrying information encoded at the bounce point. Or they might be entirely new, created fresh in our current cycle. This leads to a strange possibility. In an eternally bouncing universe, light might be eternal in a different sense than in heat-death. Not eternal as an unchanging dilute field approaching zero energy, but eternal as a cyclically varying field that repeats the same pattern every cycle. The photons are created, travel, compress, bounce, expand again, in an endless cycle with no true beginning or end. But cyclic cosmologies face a serious problem. The second law of thermodynamics. Entropy increases in every cycle. Even if the bounce resets expansion and redistributes matter, it cannot decrease entropy. Each cycle must have higher entropy than the previous one. Eventually, after enough cycles, the universe reaches maximum entropy and can no longer bounce. The cycles must end. Unless something resets entropy at each bounce, which would require physics beyond anything currently understood. Entropy is perhaps the most fundamental constraint in all of physics. Finding a mechanism to decrease it without violating the second law is extraordinarily difficult. Most physicists are skeptical that cyclic cosmologies can avoid the entropy problem. So even in the bouncing scenario, the cycles likely end eventually in heat-death. After countless cycles of expansion and contraction, of creation and destruction, of photons bouncing between high and low energy states, entropy finally maximizes and the cycles stop. What remains is the same state described earlier. Maximum entropy, minimum useful energy, photons dissolved into vacuum fluctuations, time losing its meaning. The bounce delays the inevitable but does not prevent it. Unless physics contains surprises beyond our current understanding, Unless new principles emerge at the intersection of quantum mechanics and gravity, unless reality is stranger than our theories suggest, all roads seem to lead to the same destination. Maximum entropy, heat death, the final dissolution of light into quantum vacuum noise. But one more scenario deserves consideration. What if the universe does not end at all? What if expansion continues forever, but new universes somehow emerge from the vacuum? What if eternal inflation is correct, and our universe is just one bubble in an infinite multiverse, where bubbles constantly form and evolve and generate new bubbles? In eternal inflation, the universe never truly ends because it never existed as a single entity. Our observable universe is a pocket within an eternally inflating space. Inflation continues forever in most of the volume, but occasionally inflating fluctuates and inflation ends locally, creating pockets like ours where expansion slows and matter forms and galaxies evolve. In this scenario, our pocket universe might end in heat death while inflation continues elsewhere. Other pockets form, evolve, and end in their own heat deaths. The multiverse as a whole expands eternally, generating infinite pockets, but each individual pocket follows the same trajectory toward maximum entropy. What happens to light in this scenario? Within our pocket, photons follow the heat death trajectory described earlier. They redshift, dilute, dissolve into vacuum fluctuations. But in other pockets, new photons are constantly being created as new stars form and new galaxies evolve. The multiverse as a whole contains an infinite and eternal supply of light, even though any particular pocket eventually goes dark. Does light from our pocket influence other pockets? Generally, no. The pockets are causally disconnected. Light cannot travel between them. Each pocket is its own universe with its own physics and its own light. A photon born in our universe will never reach another universe. It is confined to our pocket, destined to fade as our pocket ages toward heat death. But there might be exceptions. Some models of eternal inflation allow rare collisions between bubble universes. If two pockets happen to form nearby in the inflating space, they might collide before expanding apart. Such a collision would have dramatic observational consequences, potentially leaving imprints on the cosmic microwave background. If a collision occurs, photons might pass between pockets. Light from one universe might enter another. This is highly speculative, but it suggests that light's fate might not be entirely confined to a single universe. Some photons, extraordinarily rare ones, might escape to other universes and continue their journey there. But for the vast majority of photons, the pocket universe they are born in is the pocket universe they die in. They cannot escape. They are bound by the expansion of their own pocket, destined to fade as that pocket reaches maximum entropy. These various scenarios, heat death, big rip, big crunch, big bounce, eternal inflation, represent the main possibilities according to current cosmology. Each offers a different fate for light: gentle dissolution, violent destruction, compression to a singularity, cyclical transformation, confinement to an isolated pocket of a multiverse. Which is correct? Current observations favor heat death within an eternally inflating multiverse. Our pocket universe seems destined to expand forever, cool forever, eventually reaching maximum entropy. But observations cover only a tiny fraction of cosmic history. We extrapolate boldly into the far future based on limited data. We could be wrong. What we can say with confidence is this: light does not last forever in any scenario. In heat death, it dissolves into vacuum. In big rip, it is torn apart. In big crunch, it is compressed to a singularity. In big bounce, it might survive cyclically but eventually faces heat death when cycles end. In eternal inflation, it fades in each pocket even as new light appears in other pockets. No scenario offers true eternity for any particular photon. No scenario allows light to travel forever unchanged. The universe, in all its possible endings, eventually transforms light into something else or reduces it to irrelevance. This is not what our intuition suggests. Light seems so fundamental, so persistent, so immune to change. It travels at the cosmic speed limit. It passes through vast distances unaffected. It seems eternal, but eternity is a long time. Longer than stars burn, longer than black holes evaporate, longer than atoms remain bound. And across the true timescales of cosmic evolution, even light transforms. Even photons change. Even the fastest thing in the universe reaches an ending. We have followed light through every possible ending the universe might face. We have seen it dissolve into vacuum noise and heat death, torn apart in the Big Rip, compressed to a singularity in the Big Crunch, transformed cyclically in the Big Bounce. Each scenario reveals something about light's nature, but together they reveal something deeper about existence itself. Light is not just electromagnetic radiation. It is not just photons traveling through space. Light is information, connection, causality, the phenomenon that allows distant events to influence each other, that carries data about the past into the future, that makes observation and measurement possible. When we ask where light goes when the universe ends, we are really asking what happens to information, causality, and the very possibility of events when the cosmos reaches its final state. Consider what light does in the universe we currently inhabit. Every time you see something, photons carry information from that object to your eyes. The color tells you about temperature and composition. The brightness tells you about distance and luminosity. The spectrum reveals motion through Doppler shift. Light is how the universe communicates with itself, how one region of space shares information with another. This communication requires several things. It requires a source that emits photons. It requires a medium, space itself, through which photons can travel. It requires a receiver that can absorb photons and extract information from them. And crucially, it requires time, a duration during which the photon travels from source to receiver. In heat death, all of these requirements fail. Sources have exhausted their energy. Photons are so stretched and diluted that they carry effectively zero information. No receivers exist because no complex structures can form at maximum entropy. And time, in the sense of change and evolution, has stopped because entropy cannot increase further. Light still exists, technically. The photons are still there as quantum states of the electromagnetic field. But communication has become impossible. Information transfer has ceased. The function that light serves, connecting distant regions and enabling causality, no longer operates. This is what truly dies when light fades to nothing. Not the photons themselves, which are conserved by fundamental laws, but the network of communication and causality that light enables. The universe becomes fundamentally disconnected. Events cannot influence other events. Information cannot propagate. The cosmic web of cause and effect collapses. Without light, or rather without functional light capable of carrying information, the universe becomes a collection of isolated quantum states with no way to interact. Each region of space exists independently, cut off from all others by the impossibility of communication. The cosmos fragments into an infinite number of causally disconnected points. This raises a question that physics cannot fully answer, but philosophy must confront. Does the universe still exist in any meaningful sense when nothing can observe it or interact with anything else? Quantum mechanics gives observation a privileged role. The act of measurement affects quantum systems. Before measurement, systems exist in superposition, spread across multiple possible states simultaneously. Measurement collapses the superposition, forcing the system into a definite state. This is not just an epistemic issue, a matter of what we know. It is ontological, a matter of what exists. In the current universe, observations happen constantly. Photons interact with matter. Particles collide. Measurements occur whether or not humans are present to interpret them. The quantum world is constantly being observed and measured by itself, by the interactions between its constituent parts. But in heat death, interactions cease. Photons are too dilute to collide with anything. Particles are separated by distances exceeding the current observable universe. Nothing measures anything. No observations occur. No wave functions collapse. Does this mean the universe exists in pure superposition? Does everything become quantum potential without definite actuality? Does the distinction between possible and actual lose meaning when nothing can make that distinction? These questions touch the foundations of quantum mechanics and the nature of reality itself. Different interpretations of quantum mechanics give different answers. In the Copenhagen interpretation, measurement is fundamental and reality only exists when observed. In heat-death, this would mean reality itself fades, leaving only mathematical potentiality. In the many worlds interpretation, all possibilities coexist in different branches. Heat-death would simply be one branch among infinite others, no more or less real than any alternative. We cannot answer these questions with current physics, but they reveal something important about light's role in the universe. Light is not just stuff, not just particles obeying equations. Light is the mechanism by which quantum potentiality becomes classical actuality, by which superpositions collapse into definite states, by which information propagates and measurements occur. When light fades to irrelevance in heat-death, the mechanism of actualization fades with it. The universe might continue existing mathematically as solutions to quantum field equations, but whether it exists physically as definite states with definite properties becomes unclear. Now consider the arrow of time more deeply. We experience time as flowing from past to future. Memories exist of the past, but not the future. We can influence the future, but not the past. This asymmetry seems fundamental to existence, but it arises entirely from the second law of thermodynamics. Entropy increases from past to future. That is the only fundamental difference between the two directions of time. The equations of physics are mostly time, reversible. Swap past and future, run the movie backward, and the equations still work. Maxwell's equations for electromagnetism work equally well forward and backward in time. A photon traveling from A to B could just as easily travel from B to A. The physics does not distinguish between these scenarios, but thermodynamics does. Entropy increases in the future direction, not the past direction. This provides an arrow, a preferred direction for time. And this arrow determines everything about our experience of temporality. In heat-death, entropy has maximized. The arrow has reached its target. No further increase is possible. And without increasing entropy, there is no way to distinguish future from past. The arrow of time has not reversed or disappeared. It has simply pointed at everything simultaneously because all states have maximum entropy. What does this mean for light? Photons still propagate, but their propagation no longer distinguishes past from future. A photon moving from here to there is equivalent to a photon moving from there to here because both scenarios have identical entropy. The distinction between source and receiver, between emission and absorption, loses physical meaning. In this timeless state, light becomes truly eternal in the sense that it exists outside of time. Not eternal meaning lasting forever. Eternal meaning existing in a state where time does not flow, where past and future are indistinguishable, where duration has no meaning. This is perhaps the strangest fate for light. In our current universe, photons are intimately connected with time. They travel at the speed that sets the cosmic clock. They experience no time in their own reference frame, but enable time for everything else by carrying causality from event to event. In heat-death, they persist, but time does not. They exist, but cannot change. They propagate, but accomplish nothing. There is a profound loneliness in this image. A photon traveling through maximum entropy space has no past it came from and no future it is going toward. It simply exists, unchanging and unchangeable, in an eternal present that stretches infinitely in all directions with no events to mark it and no observers to notice it. Human consciousness, which relies so heavily on light for perception and which exists so deeply embedded in time's flow, cannot easily grasp this state. We are temporal beings. Our thoughts unfold sequentially. Our memories distinguish past from present. Our anticipations project into the future. The very structure of consciousness depends on the arrow of time. In a universe without time's arrow, could consciousness exist? Almost certainly not. Consciousness requires creating memories, forming thoughts, processing information. All of these increase entropy locally even if they are powered by processes that increase entropy more globally. At maximum entropy, no local decreases are possible. No information structures can form. No thoughts can occur. No consciousness can exist. This means that the end of light's meaningful existence coincides with the end of all possible observers. No one will be present to witness the final photon becoming indistinguishable from vacuum noise. No consciousness will experience the transition to timelessness. The universe will end not with anyone noticing, but with the permanent impossibility of anyone ever noticing anything again. There is something deeply melancholic about this realization. Light, which enables sight and awareness and connection, fades into irrelevance at exactly the moment when nothing remains that could see or be aware or connect. The last light and the last observer disappear together, or rather, the last light becomes unobservable at the same moment that the last observer becomes impossible. But perhaps there is also something beautiful in it. The universe, in heat death, achieves a kind of perfect stillness. All striving ends. All struggle ceases. The cosmic machine, which has been running since the Big Bang, converting energy from useful to useless forms, finally stops. Not because it broke down or ran out of space to operate in, but because it completed its task. It maximized entropy. It explored all possible states. It reached the natural endpoint of physical law. In this state, the universe rests. Not the rest of sleep, which is temporary and from which one awakens. The rest of completion. The rest of having nothing left to do because everything that could happen has happened. The rest of perfect equilibrium where all forces balance and all gradients have flattened. Light participates in this rest. The photons that raced across cosmic distances at maximum speed, that carried information about stellar birth and galactic evolution, that connected causally distant events into a coherent history, finally stopped their journey not by arriving anywhere, but by the journey itself becoming meaningless. They reach no destination because destinations require difference, require some place that is not here, and in maximum entropy everywhere is the same. This is light's final transformation, from photon to quantum potential, from information carrier to vacuum fluctuation, from connection to isolation, from time-bound traveler to timeless mathematical state, not destroyed but dissolved, not ended but transformed beyond all recognition or function. And perhaps this is the fate of everything, not just light. Stars dissolve into radiation, which dissolves into vacuum noise. Black holes evaporate into photons which stretch into irrelevance. Matter decays, if protons are indeed unstable on long enough timescales, leaving nothing but radiation which itself fades to nothing. The entire material universe, everything that ever existed in any form, might ultimately suffer the same fate as light. Dissolution into the quantum vacuum. Transformation into mathematical potential with no physical actuality. If this is true, then asking where light goes when the universe ends is really asking where everything goes. And the answer is the same. Into a state of maximum entropy where existence becomes indistinguishable from non-existence, where being reduces to pure mathematical possibility, where the physical universe dissolves into the space of all possible quantum states, without anything to collapse those states into definite reality. This is not quite non-existence. Energy is conserved. Information might be preserved in some abstract sense. The quantum states that describe photons and particles and fields all still satisfy the equations of physics. In the mathematical sense, everything still exists. But mathematics is not enough for existence in any meaningful sense. Existence requires actuality, not just possibility. It requires definiteness, not just superposition. It requires the ability to affect and be affected, to participate in causal chains, to make a difference. In heat death, nothing makes a difference anymore. Nothing affects anything. No causal chains unfold. Existence becomes purely formal, purely mathematical, purely abstract. The universe exists in the same way that the number 3 exists or the concept of justice exists. As an abstraction, a pattern, a set of relationships described by equations, but not as a physical reality with definite states and actual events. Light's journey ends in this abstraction, from concrete photon to abstract mathematical potential, from thing to concept, from reality to possibility. The final transformation is not from something to nothing, but from something to everything, and nothing simultaneously, a quantum superposition of all possible states with no observation to collapse it into actuality. This is where light goes when the universe ends, not into darkness, because darkness implies an absence that could be filled, not into nothing, because nothing implies a negation of something, into a state that transcends the distinction between light and darkness, between something and nothing, between existence and non-existence. A state that mathematical physics can describe, but human language struggles to name. Perhaps the only appropriate response to this realization is silence. The same silence that pervades the heat-death universe. The silence of no events occurring, no information propagating, no time flowing, no observations happening. The silence of completion, of rest, of endings that are so final they erase even the possibility of new beginnings. And yet, we are here now, in a universe young enough that stars still burn, in an era early enough that light floods space from countless sources, in a time when photons carry information and enable sight and connect distant events into coherent narratives. The heat death is trillions upon trillions of years away. For now, light persists. For now, it travels. For now, it matters. This is the final truth about light's fate. Yes, it will eventually fade into irrelevance. Yes, the universe will reach maximum entropy. Yes, all sources will exhaust themselves and all photons will stretch into vacuum noise. But not yet. Not for timescales that make the current age of the universe seem like an eye blink. Not while stars still burn and galaxies still evolve and black holes still swallow matter and convert it into Hawking radiation. For now, every photon that enters your eye carries a story. Light from the sun traveled 8 minutes through space to reach you. Light from Alpha Centauri traveled 4 years. Light from the Andromeda galaxy traveled 2.5 million years. Light from the most distant galaxies we observe traveled more than 13 billion years, showing us the universe as it was in its infancy. Each photon is a messenger from the past. Each carries information across time and space. Each connects you to distant events that happened long before you existed and will continue influencing the universe long after you are gone. Light is the thread that weaves the universe into a coherent whole, connecting all events and all observers into a single causal tapestry. This tapestry will eventually unravel. The threads will stretch until they break. The connections will fade until they disappear. The coherent whole will fragment into isolated points with no communication between them. Light's journey will end not with a destination, but with the dissolution of journeying itself. But that ending, however inevitable, does not diminish the beauty of the journey. Light has been traveling since the beginning of time. It will continue traveling until time loses meaning. And in the incomprehensible span between beginning and ending, photons will carry stories, connect events, enable observation, make causality possible, and weave the universe into something more than just a collection of isolated quantum states. Where does light go when the universe ends? It goes where everything goes, into the state of maximum entropy where all distinctions fade and all processes cease and existence becomes indistinguishable from the mathematical space of possibilities. It goes into a silence so complete that the word silence itself loses meaning. It goes into a rest so final that rest is no longer distinguishable from action, stillness from motion, being from non-being. And in that state, the photon that entered your eye carrying information about a distant star, the photon that traveled for millions of years through the void of space, the photon that existed for no time in its own reference frame, but for eons in yours, finally ends its journey. Not by arriving anywhere, but by the concept of arrival itself becoming meaningless in a universe where everywhere is the same and every time is now and always. This is the fate of light. This is the fate of everything. Dissolution into timeless, spaceless, eventless mathematical potential. A return to something like the quantum foam from which the universe emerged at the Big Bang. Not a reversal, because time does not reverse, but a completion of the cycle from low entropy to high entropy, from order to disorder, from structure to formlessness, from actuality to potentiality. And perhaps, in ways we do not yet understand, from that potentiality something new might emerge. Not in our universe, which will have reached its final state, but in other universes, other pockets of inflation, other quantum fluctuations in the eternal multiverse. The photons of our universe will fade to nothing, but photons in other universes will continue traveling, carrying information, enabling causality, weaving new tapestries from new threads. Light is not eternal, but the possibility of light might be. Not in the sense of specific photons lasting forever, but in the sense that the laws of physics that allow light to exist, that permit electromagnetic radiation and quantum field excitations and information propagation, might be eternal features of reality itself. Our light ends, but the light, allowing structure of physics persists. This is cold comfort perhaps. The specific photons that matter to us, that carry the stories of our stars and our galaxies and our era, will not survive. They will dissolve into vacuum noise along with everything else we know. The heat death of our pocket universe is final and irreversible for everything within that pocket. But the multiverse might be infinite and eternal. Other pockets might be forming constantly. New universes might be emerging from quantum fluctuations in the inflating space. And in those new universes, new light will travel, new photons will carry new information, new observers might witness new stars burning in new skies. Our light ends. But light itself, as a possibility, as a feature of physical law, might never end. It might be recreated infinite times in infinite universes, each instance temporary, but the pattern eternal. And with that thought, perhaps we can find peace with light's fate. Yes, it will fade. Yes, our universe will reach heat death. Yes, every photon we have ever observed will eventually stretch into irrelevance. But the pattern persists. The possibility remains. The laws that allow light to exist are, perhaps, eternal features of reality itself. The photons that enabled you to read these words will eventually fade. But photons, as a concept, as a quantum state, as an excitation of the electromagnetic field, will continue to exist in the abstract space of physical possibilities. And in universes yet to be born, those possibilities might become actual again, creating new light for new observers in new eras of cosmic history. This is where light goes when the universe ends. Into memory, into potentiality, into the eternal space of physical law from which new light might someday emerge. Not preserved, but recyclable. Not immortal, but endlessly renewable. Not eternal, but eternally possible. And for now, while we exist in this brief era when stars still burn and photons still flood space, we can appreciate light for what it is. The fastest thing in the universe, the carrier of information across cosmic distances, the thread that weaves reality into coherence, the phenomenon that connects us to stars we will never touch and times we will never see. Light's journey will end, but for now, it continues. And that continuation, however temporary, however destined to fade, is enough. More than enough. It is everything we have and everything we need to understand our place in the cosmos and our connection to the vast, ancient, beautiful universe that surrounds us. The universe will end. Light will fade. Entropy will maximize. Time will lose meaning. But not yet. Not while stars still burn. Not while photons still travel. Not while we are here to witness and wonder at the extraordinary phenomenon of light carrying stories across the incomprehensible distances of space and time. For now, the journey continues. The photons travel. The light shines on. And that is enough.